the word IBM written with xenon atoms. This is a very famous image. If you look at IBM webpage, it was actually done by this technique, STM. The idea is that an atom will be delivering or enabling more current to go through than the vacuum around it. So it looks like a bright spot. This is what we do here. So you can use it for silicon, you can use it for germanium, you can use it for any atom that is a bit conductive. You can also use it for organic molecules. What I want to show you here, because this is actually really the future of electronics. As you all know, we're getting very close to the limits of the physical limits of making the material we have now, silicon, to function correctly in a processor. The only way to go forward is to come up with new material that is going to behave exactly the same as silicon, but on a small dimension. And most scientists see that the solution is in organic electronics. How to use organic molecules to function exactly the same as silicon material. What you see here is this molecule. We have a benzene ring. All of us during high schools, we've always been told a benzene ring. Okay? Well, it actually does look like a ring. That's a benzene ring there. This is a row of benzene rings from this molecule aligned there. And this is another row. And this is another row. When we say alkyl chain, it actually does look like a chain. These are chains of carbon atoms, these carbon atoms. Now, how precise this technique is that you can actually count. There is 11 carbon atoms here. You can count 11 carbon atoms. So you can actually see where the atoms are and how they are aligned. This is also a fluorinated atom, and what you can see here is that if you have a fluorinated atom, it becomes dark. Now, this technique allows us to look at things very simply on the surface, on a sub-nanometers distance, because the distance between each two atoms is 2.5 nanometers. So you can actually see in between, which is a sub-nanometer scale. Now, how does this work? This is really where the whole idea, the difference between quantum physics and classical physics takes place. Now, classical physics says if you have two surfaces, the electronic wave function will decay as soon as you get to the surface and will just go to zero. Quantum physics says no. Quantum physics says no, there is actually a decay, a gradual decay of the electronic wave function. This is the theory behind the STM, all right? So, if we can actually bring these two electrodes close enough so that these two decaying wave functions can actually meet, then the electrons can tunnel. This is where the word tunneling comes from. When we say scanning, tunneling, microscopy. The word tunneling comes because we bring these two surfaces, the tip and the surface, very close to each other, that the electrons will tunnel across a barrier that we have here. Now, how can we use this? If there is a molecule on the surface, we can actually look at the electronic structure of the surface, whether we are looking at the occupied state or the empty states. And this is what you see here in this image. We are looking we're not seeing the atom, we're looking at the electronic clouds, we're looking at the local density of state of the atoms, of the electrons around the atom. Now you will say, I'm an engineer, why am I looking at this? Right? Let me show you an example. Why do you need to be knowing how does a molecule look like and what is the electronic states around the atom? This is a molecule called oligocyphene. Forget the name, okay? Don't worry about the name. But what it has 5 membered rings with sulfur. This molecule is the future of wiring on the board. It has a very high charge mobility. It's very stable on the surface in ambient conditions. So basically the idea is that if you want to make everything very small, you also need to connect all your components. And the idea is to build organic molecular wires. And this is what you're doing here, is by using chemical reactions, you take this molecule. What you're seeing here is that each yellow circle here is 2 of these molecules aligned against each other. And by a chemical reaction, they start to change from this state to this state, actually building a molecular wire. The width of this wire is less than 2 nanometers. That's a molecular wire, 2 nanometers on the surface. So So this will solve a problem when you start trying to connect things with silicon, and silicon doesn't work anymore because it's just too thin, or copper, or any other material. This is one of the solutions. Now, STM is very important and very nice for a lot of electronic work, but it's not the optimal technique for a lot of other applications because everything must be conducting. So the same team invented what is called the atomic force microscopy, and basically what you have is that you have a tip over here that scans on the surface with attraction and repulsion forces, and it's followed up by a laser. I'm not going to go too much into these details, but what you need to know is this is the shape, different shapes of the tip that is here on the surface. Now again, just before we go into this, a lot of people will say, well, that is science, we're engineers, we want to see practical applications. Well, IBM, again, has done an application to show you what is it that you can do with this technique, the atomic force microscopy. So again, this is from IBM, and by the way, this is about 1999, 2000, this is not something new. What we're going to see is that a lot of these AFM tips used as a memory device to save, to write to a surface, zeros and ones. Basically what you're seeing here is hundreds and thousands of these AFM tips I showed you earlier in the previous slide, and they're all lined on the surface, and we're going to zoom in on one of these now and look at how it looks on the surface. The surface is made of a polymeric material, and the tips are scanning on the surface. So what we're going to see right now is a write operation. How do we write on the surface? Basically applying a bit of electricity across the tip. The tip heats up. So we apply electricity from here, the tip heats up, becomes a bit warm, and then it can actually, as you see, it punctures the surface, writing a 0 and a 1. So an empty area is a 0, a hole or a valley is a 1. Okay? This is in a polymeric surface. Now, the AFM can read these dimensions. By the way, the dimension of this valley is about a few nanometers wide. Okay? So you can put billions of bits of information on this. Now it is reading on the surface, as you can see, as it goes down and up. This is the laser here. The laser reflection changes, so we know that there's actually a 0 or a 1. A write operation, an erase operation is simply, and this is from surface chemistry. Actually, if any of you have a car and has a small bump, will know exactly what these guys are doing. Simply by trying to hit right close to where the valley is, you can actually erase the valley, as you can see. If you keep doing that, you're erasing the actual valley right next to it, and by lowering the amount of the size. Now, is this a product out in the market, or is this science fiction? This is actually a product the guy who has the camera there is probably using. This is an SD flash memory. Okay? So, nanotechnology is not science fiction, and these techniques are important for you guys as engineers to actually know how they build these things. Now, using this AFM, one of the ways to look at material is actually looking at this chemical compound, which has a lot of excitement for a solar energy application, and looking at, can we actually make from this molecule a rope, and look at the rope. I'm not going to go into deep details, but what I want you to notice is that we can actually see the bundling around the rope. What you see here is the nodes in the rope of this molecule aligned right next to each other, and we can actually see that at these nodes there is a higher transmission of light energy going through. Now I'm going to jump to a different area of nanotechnology. We've talked about what is the definition of nanotechnology. We've talked about STM, which is credited for the birth of nanotechnology. I've talked about AFM, which overtakes some of the problems that the STM cannot solve. And now I'm going to look at a different thing, something called single molecule spectroscopy. And again, I'm going to demonstrate to you why this is important for engineers. Now, I'm not going to go into deep details of this. What I want you to look at is this image. Now, what is blinking here, these are actually single atoms or single quantum dots. And what you see is under continuous irradiation with laser. Normally, we should see these molecules bright all the time because they're continuously pumped with energy.